Welcome back to the deep dive. Today, we're tackling a really cutting-edge area, using machine learning to understand how treatment effects differ, you know, from person to person.
Yeah, absolutely. And this is so crucial for moving towards like truly personalized approaches.
Right, in fields like medicine, policy, that sort of thing. We've got a stack of research and notes here, and our mission is really to pull out the key insights.
hmm
We'll be focusing, as always, on the technical side, the details, and what it all means for advancing these fields.
Exactly. See, the big challenge really is figuring out who benefits most and maybe by how much from a particular intervention.
Right.
And it gets incredibly complex when you have, well, a lot of different factors to consider for each individual, or maybe when the data we have isn't quite as extensive as we'd hope.
And it turns out there's maybe a clever way to get better at this using something called side information.
That's the idea.
So we're going to explore how a technique called pre-training can significantly improve our ability to estimate these individual treatment effects.
Yeah, the core idea is that by understanding the link, the relationship between what generally predicts an outcome and what predicts whether a treatment will work differently for different people,
Oh, okay.
we can potentially get much more accurate and reliable results.
Got it.
So we'll be diving into these pre-training strategies, looking at how they smartly exploit this connection to give us more robust estimates of conditional average treatment effects, or CATE.
Kate, right.
We'll be getting into the technical details and, importantly, what these advancements might mean for the future of personalized interventions.
Okay, let's unpack this a bit more then. Why is understanding these varying treatment effects, this Kate, why is it so vital? Why isn't just knowing the average effect good enough?
We'll think about, say, a new medication. Clinical trials might show that, okay, on average, patients improve.
Sure, the standard result.
But the reality is, some individuals might see dramatic benefits, others may be a modest change, and, well, sadly, some might not respond at all.
Or even have negative effects.
Or even experience side effects that outweigh any potential gain. Exactly. So if we only look at that average effect, we risk, giving a treatment to people who won't benefit,
Mm-hmm.
and maybe potentially withholding it from those who really would.
Mm-hmm.
We need to understand the nuances.
So the average is maybe a good starting point, but we really need to zoom in, get more granular to make truly informed decisions.
Precisely. I mean, we can't directly see how a treatment would affect every single person in all possible scenarios. That's the individual treatment effect, or ITE, which is sort of the holy grail but unobservable.
Oh.
But what we can estimate is the conditional average treatment effect.
Yeah.
Still an average, yeah, but it's an average for a specific group of people who share similar characteristics.
Like their age or genetics or lifestyle factors.
Exactly, things like that. And by looking at more and more of these characteristics, these covariates, we can get a much finer-grained picture of how treatment effects actually differ across the population.
Okay, and this is where the power of large data sets and machine learning really comes into play.
Absolutely.
Mm-hmm.
We're seeing this explosion of large-scale observational data, and this gives us the potential, at least, to estimate CATE for very specific groups.
Mm-hmm.
And machine learning provides us with the tools to analyze this complex data.
Mm.
Methods like lasso boosting, neural networks, random forests, they're proving incredibly useful for teasing out these heterogeneous effects.
And these can be part of bigger frameworks too, right? These
Yeah.
meta-learners.
Yeah, exactly. Meta-learners are basically frameworks that cleverly break down the pretty difficult problem of estimating treatment effects into smaller, more manageable prediction tasks that these ML methods are good at.
But it's still a tough problem, isn't it? Finding these differences. You mentioned it can be like finding a needle in a haystack.
It really can be,
Is it?
especially when we don't have a huge amount of data for every possible subgroup. Imagine you have hundreds, maybe even thousands of different characteristics you could look at.
Mhm.
Trying to figure out which combination of those characteristics truly influences how someone responds to treatment, it becomes incredibly challenging, particularly if the true differences are subtle or if our data set isn't massive.
So you run into statistical power issues.
Exactly. You might not have enough power to detect real effects, or worse, you might end up with models that just fit the noise in your data rather than the true underlying patterns. Overfitting becomes a real risk.
Okay, so how does this idea of shared support help us find that needle? What does that term really mean here?
Right. So shade support, the concept is about finding common ground. an overlap between factors that tell us something about a person's likely outcome regardless of the treatment.
Okay, the general prognosis.
Yeah, we call those prognostic factors.
Yeah.
And factors that tell us something about how much the treatment effect itself varies from person to person. Those are the predictive factors.
Ah, so factors predicting the difference the treatment makes.
Precisely. Shared support is when there's an overlap in the characteristics that are important for these two related but distinct prediction problems.
Can you give us a concrete example, maybe from medicine?
Sure. A really great one is the protein HER2 in breast cancer.
Okay.
So women with HER2 positive breast cancer tend to have, unfortunately, a poor prognosis overall. Their cancer is often more aggressive.
So HAR2 is prognostic.
It's prognostic, exactly. But, and this is the crucial part, HER2 expression also strongly predicts whether a patient will respond well to therapies specifically designed to target the HER2 protein like Herceptin.
Ah, okay. So it does both jobs.
It does both jobs. It's prognostic for the natural course of the disease, and it's predictive of how effective a specific treatment will be. The National Cancer Institute actually has definitions for these. Prognostic tells you about the likely disease course independent of treatment. Predictive tells you about response to a particular treatment.
That makes a lot of sense. Are there other examples where we see this kind of overlap, the shared support?
Oh, absolutely. It's not just single biomarkers. We see it with more complex measures, too, like gene expression signatures in cancer. Certain patterns of gene activity might indicate both a higher risk of the cancer coming back and a greater likelihood of responding to a specific chemotherapy.
Interesting.
Or think about, say, the link between depression and cardiovascular disease. Depression is a known risk factor for heart problems that's prognostic,
Mm-hmm.
but it can also affect how well patients stick to their heart medication regimens, which then influences the treatment's actual effectiveness, so it becomes predictive too, indirectly.
Wow. Okay. Even in other fields, like education.
Yeah, potentially.
Yeah.
A student's prior academic performance, for instance, that likely predicts their overall success, right, the prognostic.
Sure.
But it might also influence how much they benefit from, say, a new teaching method or an intervention compared to other students, making it predictive as well.
You also mentioned selection factors earlier. How do they fit into using this side information?
Right, selection factors. These are characteristics that influence which treatment a person actually ends up receiving, especially in situations where the treatment assignment isn't purely random, like in observational studies.
Okay, so why someone got the treatment in the first place?
Exactly. For instance, doctors might be more likely to prescribe a newer, maybe more aggressive drug to patients they believe are more likely to benefit, perhaps because they're younger or have a specific disease subtype.
Mm-hmm.
In that case, the factors guiding the doctor's decision, the patient's age, their condition severity, other health issues, these selection factors can also be predictive of how well that patient will actually respond to the treatment they received.
Huh. So the very reasons someone gets a particular treatment might give us clues about how effective that treatment will be for them.
Precisely. It's a potential source of information. We sometimes see this in clinical trials too, maybe in the control arm where doctors have some discretion, like choosing the best available treatment or physician's choice.
Ah,
The factors that influence that choice could also be related to who ultimately benefits most from which option. And you can imagine this being relevant in education too. Maybe socioeconomic background or motivation influences participation and moderates the benefit of an intervention.
okay, this is really helpful context. So we've got these factors, prognostic, predictive, sometimes overlapping, and these selection factors. Now, how do we actually use this information to get better CATE estimates? You mentioned pre-training the R learner with Lasso. Let's break that down.
Okay, yeah, so the R learner is a specific statistical framework, one of the meta learners, designed particularly for estimating CAT.
Mm-hmm.
The key idea behind pre-training here is that we can use information learned from one prediction task to help improve another.
Transferring knowledge, basically.
Kind of like transfer learning, yeah.
Yeah.
In this case, we're using what we learn from predicting the average outcome, the prognostic part, to improve our ability to predict how the treatment effect varies the predictive part.
And Lasso is the tool you're using for this.
Right. We're focusing here on using the lasso, which, as you know, is a popular method for doing variable selection and regularization simultaneously. It helps prevent overfitting, especially with many potential predictors.
Okay, so what are the actual steps? How does this pre-training process with the R Lasso work in practice?
It's essentially a two-step process. First, we fit a lasso model to predict the average outcome for a person, MX, ignoring the treatment for a moment. This step helps us identify which factors, which covariates, seem generally important for predicting the outcome overall.
So finding the prognostic signals.
Exactly. And the lasso coefficients give us an idea of the strength of those relationships too. Then second, we fit another model, specifically designed to estimate the CATE. And we use a special objective function for this called the R-loss, which is tailored for CATE estimation.
Okay, and this second model is also a lasso. You mentioned adaptive lasso.
Yes, we use an adaptive lasso in the second step. The adaptive part is key.
What makes it adaptive?
It builds on the standard lasso by applying different penalties to different variables.
Mhm.
And crucially, these penalties are based on the results from that first step, the prognostic model.
Ah, okay. How does that work?
Well, for the factors that the initial lasso model flagged as being important for predicting the average outcome.
The ones that didn't shrink to 0.
Right. For those, we apply a smaller penalty in the second CATE estimating step. But for the factors that were deemed unimportant in the first step, the ones lasso zeroed out, we apply a much larger penalty.
So you're encouraging the CATE model to pay more attention to the factors that already showed some general relevance to the outcome.
Precisely. It's like you're giving it a hint. Hey, these factors seem to matter for the outcome in general, so they're probably a good place to start looking for treatment effect differences.
That's clever. And you can control how strong that hint is?
Yes, exactly. There's a parameter, let's call it alpha, that controls this pre-training strength. If alpha is high, the penalties in the second step are pretty similar for all variables, less pre-training influence. But as we lower alpha, the penalty on those variables not selected in the first step gets much, much stronger. It really pushes them out of the CATE model, focusing it on the potentially shared factors.
And how do you pick the right alpha?
Well, interestingly, we found that we can actually use the R-loss itself, calculated on the training data, to help tune alpha. We look for the alpha that minimizes this R-loss, aiming to find that sweet spot for the pre-training strength.
Nice. And does this idea apply only to the R learner?
No, not necessarily. The same general principle, leveraging information from predicting the overall outcome, or maybe the outcome under control, could potentially be applied to other CATE estimation frameworks, like the DR learner, for example.
Okay, so what did your simulations show? Did this pre-trained R lasso actually perform better?
Yeah, we ran simulations designed to mimic a randomized trial setting, binary treatment, various covariates influencing both the outcome and the treatment effect. And we saw a pretty clear pattern. As the amount of shared support, the overlap between the important prognostic factors and the truly predictive factors increased.
Right.
The pre-trained R lasso became significantly more accurate in estimating CATE. Its mean squared error, the MSE, dropped noticeably.
And this was especially true with stronger pre-training, lower alpha.
Yes, particularly when there was substantial overlap. Using a stronger pre-training signal, a lower alpha, really paid off. We also confirmed that the R-loss we calculated on the training data tracked well with the actual MSE on unseen test data.
That's good. It means the tuning process seems reliable.
Exactly. It suggests the R-loss is a useful guide for selecting that pre-training strength in practice.
You also looked specifically at the power to detect heterogeneity. Why is that important? It's not just about average accuracy.
Right. Ultimately, we don't just want a model that gives accurate estimates of CATE if heterogeneity exists. We also want it to be able to reliably tell us when heterogeneity is actually present.
To distinguish real differences from just noise.
Precisely. Assessing the power to detect heterogeneity helps us understand how well our model can differentiate between situations where the treatment genuinely has different effects for different groups versus situations where the effect is pretty much the same for everyone and any small differences we see are just random chance.
Okay, and how did you measure that power?
We used a metric derived from something called the Targeting Operator Characteristic Curve, or TOC curve.
TOC curve, like an ROC curve.
Kind of analogous, yeah. You rank individuals based on their predicted treatment benefit, their estimated KVA. The TOC curve then plots how the average actual treatment effect changes as you target treatment to groups with higher and higher predicted benefits.
Ah, I see.
And the area under this TOC curve, the IUTC, gives us a single number summarizing the model's overall ability to correctly rank individuals and identify that heterogeneity. A higher IUTC means better targeting, better detection of real differences.
And what did the simulations show for IUTC?
We ran simulations in a slightly more challenging setup, less overlap, some correlation between covariates, lower signal to noise. And the pre-trained R lasso consistently achieved a higher AUTOC compared to the standard R lasso without pre-training.
So it was better at actually finding the groups who benefited differently.
Yes, especially as we increase the sample size. It showed increased power to detect that heterogeneity.
Now, what about situations where the features, the covariates, are correlated? You mentioned lasso can sometimes struggle there. You looked at something called union lasso.
That's right. Standard lasso can sometimes get confused by highly correlated predictors. It might pick one predictor from a group but miss others, or even include some irrelevant ones just because they're correlated with the true signals. This can affect interpretability and stability.
Okay.
So to address this, researchers developed a variation called unilasso, which uses some univariate screening ideas to try and produce sparser, more interpretable models, potentially with better control over false positives.
And you applied pre-training to that, creating union lasso.
Exactly. We integrated unilasso into our pre-training framework. We compared the pre-trained R lasso, using standard adaptive lasso, with this pre-trained junior lasso.
And the results?
Performance in terms of overall accuracy, the MSE, was pretty similar between the two pre-trained methods. Both benefited from pre-training when there was shared support. But the junior lasso often produced much sparser models. It selected fewer variables. And importantly, it showed better control over the false discovery rate, FDR, and did a better job at accurately identifying the true set of predictive factors, especially with pre-training.
So potentially more interpretable and reliable variable selection with similar accuracy.
That's the takeaway, yeah. It suggests junior lasso could be a good option if sparsity and reliable identification of the key drivers are particularly important.
Okay, one final big area. Real-world relationships aren't always simple straight lines, right? How does this pre-training idea work in more complex, nonlinear settings?
That's a really crucial point. Linearity is often just an approximation.
Yeah.
So we need ways to handle nonlinear relationships between covariates and outcomes or treatment effects. One common approach is to use basis function expansions. You essentially create new features by transforming the original ones, think polynomials, splines, interactions.
Right, creating more complex building blocks.
Exactly. And then you can potentially use these new expanded features within a linear model like our pre-trained R lasso to capture nonlinear effects.
Then can you generate these basis functions automatically?
Yes, a very powerful way to do that is using tree-based methods, particularly gradient-boosted trees, like XGBoost. You can train an XGBoost model, say, on the average outcome, and then use the structure of the learned trees, the leaf nodes, to define basis functions.
Ah, clever. So the tree finds the interactions and nonlinearities for you.
Precisely. You can then feed these basis functions, maybe alongside the original features, into the pre-trained R lasso framework.
What about using tree methods directly for the CATE estimation, like random forests? Can you pre-train them too?
Absolutely. We looked at that using generalized random forests, or GRF, which are designed for CATE estimation. We explored a strategy we called pre-trained GRF.
Okay.
Here the idea is, first, you fit a random forest to predict the average outcome, MX. You get feature-important scores from that model.
Which variables mattered most for the outcome overall?
Right. Then, when you build a second random forest to estimate the CATE, BAX, you use those important scores to guide the feature sampling process within the tree building. You give variables that were important for the outcome a higher chance of being considered for splitting nodes in the CATE forest.
So again, biasing the CATE estimation towards factors already known to be relevant.
Exactly. We also looked at simpler pre-screening approaches, where you'd use lasso or feature importance scores to just select a subset of features before even training the CATE random forest.
And how did these different nonlinear pre-training strategies compare?
We tested them on various simulated nonlinear data setups, adapting some standard benchmarks. The results showed that generally pre-training helps across these nonlinear scenarios too.
Okay.
And interestingly, the approach of using XGBoost to generate basis functions and then feeding those into the pre-trained R lasso often performed very competitively, sometimes even outperforming the pre-trained random forest approaches, especially in certain settings with higher dimensions or lower signal.
So that combination seems quite powerful for nonlinear CATE.
It looks promising, yes. It combines the ability of trees to find complex structure with the regularization and variable selection strengths of the pre-trained lasso framework.
Okay, fantastic. So let's try and bring this all together. If you had to give the main takeaway from our deep dive today, what would it be?
I think the key takeaway is that we can potentially significantly improve how accurately and reliably we estimate these individual or conditional average treatment effects.
Yeah. The kitty, yeah. By intelligently using the connections, the shared support between factors that predict general outcomes and those that predict how treatment effects vary.
Hmm.
And by using these pre-training techniques within frameworks like the R-Learner, using tools like the adaptive lasso or weighted random forests or these basis expansions we just discussed, we can effectively leverage this side information.
And that helps advance personalized interventions.
That's the hope. To get closer to truly personalized approaches in medicine, education, policy, wherever understanding treatment effect, heterogeneity matters.
Of course, we should add the caveats. It's not like a magic bullet, right?
Definitely not. As we discussed, this pre-training approach really relies on there being a meaningful overlap, that shared support between the prognostic and predictive factors.
If they're totally separate sets of factors, it might not help much. Exactly. You might not see much benefit then. And also, the performance can depend on how well we can actually estimate those initial relationships needed for the pre-training step. The quality of that first stage matters. And tuning that alpha parameter using the R-loss seems helpful, but it's still something to monitor.
Makes sense. And looking ahead, what are some of the exciting next steps or future directions for this kind of work?
Well, there are several promising avenues. One big one is exploring how we can extend these pre-training ideas to use information from different, maybe much larger external data sets.
Like pre-training on a big public data set and fine-tuning on a smaller trial.
Potentially, yeah. Leveraging existing knowledge more broadly. Another really crucial step is demonstrating the real-world value. Applying these methods rigorously to actual clinical data, especially in complex areas like oncology where heterogeneity is rampant.
Showing it makes a difference in practice.
Exactly. Moving beyond simulations to real patient impact.
Fascinating stuff. So here's maybe a final thought for you listening. How might this focus on identifying shared prognostic and predictive factors actually lead us to a deeper, perhaps more mechanistic understanding of why treatment responses differ in biology maybe, or even in behavior?
That's a great point. It pushes beyond just prediction towards understanding the underlying processes.
Definitely something to mull over. It's worth digging into the research we've touched upon and thinking about the broader implications of this kind of transfer learning and statistical modeling. Thanks for joining us for this deep dive into the technical aspects of estimating heterogeneous treatment effects.